When we run a regression, we'll often see reported in the statistical output from our statistical computing software a term called the R-square. And we want to understand what that R-square means and how it's calculated and what we do with it. So you remember we run a regression, which means we're estimating the equation of a line, y equals alpha hat plus beta hat x, for example, describing a relationship between an explanatory variable x and some outcome variable y. For every observation in the data, we can then, once we've run the regression, we can then calculate a predicted y for given values of x. So we take the given value of x, xi, we subscript with the I, and we multiply it by the beta hat that we've estimated, and then we add the alpha hat that we've estimated, and that enables us to calculate a yi hat, the predicted value of y for the given value of x, predicted according to our regression line, right? So we can, once we have that predicted value of y, we can then define three terms, three numbers that we can calculate. The first is called the total sum of squares, and it's the sum of squared deviations of the y variable around its mean. So yi minus y bar squared. That's the total sum of squares. So for every observation, we take the value of the outcome, yi, we subtract the value of the mean of the y's, we square that, we add all those up together, that's the total sum of squares. In some sense, that's the total variation in the outcome that we want to explain. We have some outcome, and we want to explain it, and the sum of squared deviations is a measure of the total variation in that outcome. The next calculation we can do is the sum of squared residuals. So that's the difference between the yi's, the predicted value of y, and the actual value of y. So remember, our regression is minimizing that sum of squared residuals. That is, the alpha hat and beta hat that we estimate are chosen precisely to minimize the sum of squared residuals. Minimize doesn't mean they'll be equal to 0. If they were equal to 0, then our regression line would fit all of the points exactly. So we'd have something like this, where we had our points and our regression line fitted exactly. That would have a sum of squared residuals equal to 0 because there'd be no deviations. But normally there'll be a regression line, and there'll be our points, and there'll be deviations, right, the vertical distance here, and we add up the square of those deviations, and that's the sum of squared residuals. And then finally we have something that we might call the explained sum of squares, which is the sum of squared deviations of y, and I neglected to put the squared sign there. So it's the sum of squared deviations of or differences between the yi hat that we've estimated and the mean of y. So it's the amount of variation in y that is varying around the mean of y that's explained by our regression. So with those three terms in mind, we can then define something called the R-square as the ratio of the explained sum of squares to the total sum of squares. So it's the percentage of the total sum of squares that's explained by our regression. How much of the variation in y is accounted for by our regression line. So the explained sum of squares is just the sum of squared deviations of yi hat, our predicted y, from the mean of y, and the total sum of squares is the actual y differing from the mean of y squared. So that's our definition of R-square. Alternatively, R-square is equal to 1 minus the sum of squared residuals over the total sum of squares. So these are two alternative ways of calculating the R-square. You can see pretty easily that R-square is a number that varies from 0 to 1, and that's because the explained sum of squares can never be greater than the total sum of squares. So we have a number over a number that's greater than it, so it's always going to be less than 1. Same thing, the sum of squared residuals can never be greater than the total sum of squares, so we're always having this number be a number less than 1, so 1 minus a number less than 1 is always a number between 0 and 1. So that's our definition of r-squared. Let's actually calculate it with a simple data set. So we have some data. X is equal to 2, 3, 4, 5, 6, and then we have y's associated with each value of x. So that's our data. So we calculate the mean of x to be 4, the mean of y to be 3. Then we calculate our beta hat. So we use the simplified formula. Might be a little bit different from the one in the textbook, but you can quickly see that they're the same. And we calculate beta hat to be equal to -2. And then we calculate alpha hat, and we find alpha hat to be equal to 11. So our regression equation is y equals 11 minus 2x. So let's go ahead now that we've estimated the regression equation, we've estimated the parameters of the regression, we can go ahead and calculate the r-squared. So we're going to calculate the predicted value of yi. So if x is equal to 2, we plug this 2 into the equation, and we get 11 minus 2 times 2, 11 minus 4, so we get predicted value of y 7. If x is equal to 3, we plug that into the equation. We have 11 minus 2 times 3, 11 minus 6, so we get predicted value of y is 5. If x is equal to 4, we plug that in, and we get 11 minus 8, so y is equal to 3, the predicted value of y. If x is equal to 5, we have 11 minus 2 times 5, so it's 11 minus 10, we have y, it's 1. Now we'll take the sum of deviations of that predicted value from the actual value of y. So we take the actual value of y is 6, the predicted value of y is 7, so the difference is 1. We take the square of that, the square of 1 is 1. Here we have a difference between 7 and 5, the difference is 2, so that's 4. And we do that for the remainder, and we get the sum of all those terms is equal to 6 then. So that's the sum of squared residuals that we defined on the previous slide. So we're also going to calculate the total sum of squares. So yi minus y bar, we calculated y bar on the earlier screen. You'll remember y bar was equal to 3. So we now have, if y is equal to 6, in the first observation, 6 minus 3 is 3, 3 squared is 9. When y is equal to 7, in the second observation, 7 minus 3 is 4, 4 squared is 16, and so on. So we get a total sum of squares of 34 when we add all those up. So now we have the sum of squared residuals, we have the total sum of squares, so we have 1 minus 6 over 34, which is roughly rounded to 0.823. So that's how we calculate the r-square for a given regression. Obviously, this would be very tedious if we had a large sample size, and that's why we want to use a computer for that. Finally, one last thing, just to kind of get a visual idea. If we have a scatter plot that looks like this, where the points are sort of tightly distributed around the regression line, we're going to have a low r-square. A high r-square. If our scatter plot looks like this, so that the points are distributed sort of fairly broadly around the regression line, our r-square is going to be lower. But I want to make very clear, we don't run regressions to find the one that has the highest r-square. That is not the goal of regression analysis. And we're going to explain that and see that when we talk about multiple regression analysis. We can always add more variables and increase the r-square. That's not the goal of regression analysis, is to have a high r-square. We'll understand more about that later.